Hello, we will now do the Chapter 11 review worksheet. So if you want to try to do this as we go along, pause the video from time to time, see if you can figure out these questions, and then check your answers and send me any questions you have. That would be great. So first context is this. It says the maker of a new type of laptop computer claims that the mean battery life, it's a key word there, the mean battery life for computers of this type is 17.2 hours. You decide to test this. You take a simple random sample of 30 of these computers and get a mean battery life of 16.3 and a standard deviation of 5. And so the premise, and so the first thing you notice here is the fact that they're talking about a mean, which that means, of course, we are going to talk with Mr. T. We're going to do a T interval or a T test. And so this one, there appears to be a claim here of 17.2. And so we take a sample to test that, and we get 16.3. And so is this so different that this 16.3 would cause us to doubt or to reject this 17.2? That is the premise of a hypothesis test. And so we need to find the probability that, assuming 17.2 is true, that we would get a sample value of 16.3 or more unusual just by chance. And that probability is what we call a p-value. But first of all, let's see what's asked of us. It asks us, and then it says you perform a two-sided test of significance at alpha is 0.05. All right, so what is the name? So here's the name. So we just have one sample going on here, and it is a mean, so it's a T. So it's a T test for a mean. That is the name. Thing two. All right, so question two. What are the hypotheses? Okay, so the null hypothesis is whatever's claimed in the problem. This chapter is always going to be mu is equal to some number. Okay, that's always going to be your null. And then the alternative is going to be is going to look just the same basically, except we're replacing this equal sign with either a greater than, a less than, or not equal to. And in this case, first of all, it tells us to do a two-sided test. That means not equal to, but there's certainly nothing up here that implies go greater than or less than. Make sure you define mu. Mu is always going to be the mean something. Okay, so whenever you define mu, it is the mean something. So in this case, it is the mean battery life of all the batteries of this type, okay, in hours. So that's how you do your hypotheses. Number three says verify the conditions or the assumptions. So that means that we must sin. It says in SRS, or a simple random sample was taken, so random conditions met, okay? There must be at least 300 batteries like these for our sample size to be less than or equal to 10% of our population size. So you just multiply that sample size times 10 to get that. And then with our sample size of 30, which is greater than or equal to 30, normality is met. So any sample size 30 or more guarantees normality by the central limit term. So there's our conditions. Number four. So number four, find your test statistic, your degrees of freedom, and your p-value. So what we'll do with our calculator is we'll use our calculator to find these values. And so we shall do this. So we shall hit the stat button right there. So you hit the stat button, and then you go to test, and then you go to t-test. So this chapter is all about option 2 and option 4. So we hit enter on t-test. Now in this case, we're given stats. So we hit enter on stats, and then we enter these stats in. And so the first stat is 16.3. That's our X bar. So our null hypothesis value, first of all, is 17.2. So we enter that in. So 17.2 is our null hypothesis value. And so then our X bar is 16.3. Our S is 5. And then our sample size is 30. Our alternative is not equal to. So that's how you do that. And then we hit calculate, and that tells us our test statistic, our p-value, okay? There's our t-test statistic and our p-value. And your degrees of freedom is sample size minus 1 for a one sample deal. So that would be 29. And so that is what I wrote down here. And here I did show you the formula of how that is found, but you don't have to show the formula. You do have to recognize this formula for a t-test statistic, which you can get off your formula sheet. It's just statistic minus parameter over standard error. So it's your X bar minus your hypothesized mean, and then divided by, and then that's S over the square root of N. And so And so that's that. So we get a large p-value. And so then it says, what conclusion do you do from your p-value? And so this p-value is greater than 0.05. It's set up here at 1 as an alpha 0.05. Of course, we'd use that anyway, unless it said something different. So since the p-value is greater than the alpha, I failed to reject the null hypothesis. There is not convincing evidence that, and then you restate the alternative in context. Okay, we do not have convincing evidence that mu is not equal to 17.2 hours, and you say, what it is. So the mean life of all the batteries of this type is not equal to 17.2 hours. And interpret the p-value. So that's the conclusion with the p-value. Interpreting the p-value is to describe it as a probability, as a conditional probability. And so the p-value is, assuming the null is true, it's the probability you're going to get a sample value as unusual as the one you did, just by sampling variability. And so that's what this is saying here. If the null is true, if mu is equal to 17.2, the probability of getting a sample statistic or a sample mean of 16.3 hours or more unusual in a sample of size 30 is 0.33234. So in other words, it's reasonably plausible. Okay, so that takes us to number 7. So for number 7, it says this. It says create a 95% confidence interval with the data in context 1 and make the connection between the interval, the p-value, and the hypothesis. Remember to make an interval from last chapter. So what we would do is we would hit stat, test, and go down to number 8, which is t-interval. And the calculator went ahead and entered the data for me here, entered the x bar, the s, and the n. And so we want a 95% interval, right? Yes, we do. And so we go calculate. And so there's our interval. And so those are in essence the plausible values from mu. And the connection between that and your hypotheses and your p-value is the null hypothesis value, which is 17.2. So that is 17.2. 17.2, that is what we're testing. All right. 17.2 is inside this interval. All right, so it is a plausible value for mu and should not be rejected at 95% confidence. Make sure to put the confidence level like that. Okay, the high p-value also tells us to not reject the null hypothesis value. So that's the connection. We've done that, several times this year. So that's the connection between the interval and the hypothesized value. All right, what sort of error could you have created? All right, well, remember in regards to error, in regards to type 1 or 2 error. So my little thing, 1 is hot. Immediately when I'm asked about type 1 or type 2 error, 1 is hot. So what that 1 is hot tells me this. Type 1 error, the null is true. And it's an error, so I must have rejected it, but I rejected it. So I encourage you to write this down so you don't get it mixed up each time. And so type 2 error is the opposite of that. So type 2 error is when the null is false. Okay, and the null is false, but I failed to reject it. I failed to reject it. Reject the null. Okay, so there it is. So what sort of error could I have committed here? Well, here I did not reject the null. So it had to be, if it was any error at all, it had to be type 2 error. Type 2 error because we did not reject the null. Okay, so that takes us to number 9. Describe what type 1 error would be in this context and what is the probability of type 1 error. All right, so type 1 error would be that the null is true, but you rejected it, and the probability of type 1 error is always alpha. All right, so type 1 error is saying that the null is false when it is actually true. So it is when in fact the null is true, mu is equal to 17.2, but you say it's not. Okay, and the probability of type 1 error is always whatever your alpha is. Okay, so that is that. Okay, and that takes us to context 2. So context 2 says this. A doctor wishes to see if a new drug is effective in reducing bad cholesterol, LDL, in patients with high LDL. He has 20 patients with high LDL randomly assigned into two groups of size 10. The first group of 10 takes the new drug daily for a month and obtains the improvements in LDL shown below. The second group of 10 takes a placebo each day for a month and obtains the improvements in LDL shown below. Is there evidence that the drug is effective in improving LDL better than the placebo? A test of significance, alpha is 0.01 this time, is done. And so here's the results. Here's the amount of improvement with the new drug, and here's the improvement when they're given a placebo. And so and we're asked to do a test here. So the type of inference that we are going to do is a 2-sample t-test for the difference in means. And so that is the name of we have 2 samples. We're dealing with means, and so it's t. And so that is the name of the type of inference. Question number 2, our hypotheses. So your null hypothesis is in essence always going to be that there's no difference, that mu sub d is equal to mu sub p. Okay. So that's always going to be your null. Okay. The alternative is what you suspect might be true. And so this one, is there evidence that the drug is effective in improving LDL better than the placebo? So that means that it should have more improvements. So this is going to be greater than, where mu sub d is the mean reduction in LDL for all patients like these who take the drug. And of course, you have to say patients like these because we did not have, these 20 patients were not randomly selected. So you have to say for patients like these. Okay. And then mu sub p is just the improvement for the placebo people. All right, so verify our conditions or assumptions. And so that would be this. Okay, and so it is, remember with the 2-sample deal, it is ISIN. So it says that the 20 were randomly assigned. So the random condition is met for patients like these. Okay, and so it should say independent random. So independent random, sorry. So independent random. Independent random condition is met for patients like these. Okay. We did not have to check for our population sizes being at least 10 times our sample sizes or the 10% condition because the 20 were not randomly selected. And so then we have to verify normality. So our sample sizes are not bigger than 30. It doesn't say normality is met anywhere up here. So we have to graph the samples. So I made number lines, I graphed them. The graphs show no outliers or strong skewness, so normality is reasonable. Okay, so that takes care of that. And so then we are asked to find our test statistic, our degrees of freedom, and our p-value. And so this is how we'll do this. And so what we're going to do is we enter the data in list 1 and list 2. So I'm going to enter all this. I'm going to enter all the ones with the new drug in list 1 and all of these in list 2. So if you go stat and edit, and so in list 1, I put all the new drug and there's all the placebo. And so this is how we get our mechanics, our test statistic p-value and our degrees of freedom. So we're going to go stat, we go test, and we go down to option 4. That's the other thing in this chapter. So option 4. So we're using data this time. And so list 1 and list 2 there, the frequencies are 1. The alternative in this case is greater than. It's our alternative. We always say no to pooled, and we go calculate, and there's our test statistic, there's our p-value, and there's our degrees of freedom. Remember, with a 2-sample deal, the degrees of freedom has a complicated formula that you don't have to worry about. You just have to, you can get this off your calculator. If you don't have a calculator, you just use the smaller sample size -1. So there's your test statistic p-value and degrees of freedom right there. So those are the 3 things you have to list in your mechanics. And then what conclusion would you draw from that p-value? Well, so this p-value is less than 0.01. We used, remember, they gave us an alpha of 0.01. They gave us alpha of 0.01 in this case. So our p-value has to be below 0.01, and it is. So we reject the null. There's convincing evidence that, and then you restate the alternative. Technically, you're supposed to write all of that in context, but if you did it like this with me, that's okay. All right. So that is that. All right. And then 14, once again, making the connection with the interval, create a 99% confidence interval for the true difference and comment on the connection between the interval, the hypothesized value, and the p-value. So let's make our interval. So we'll go stat test, just like we did in the last chapter, chapter 10. And so we go down to option 0, which is the 2 sample t interval. We hit enter. And so we are using list 1 and list 2 again. We are making a 99% confidence interval. So I go 0.99 and we go calculate. And so there's the interval right there. So those are the plausible values for the true difference. And it's of note that 0 is not in the interval. So there's our interval. And you remember, so our null hypothesis is that mu sub d is equal to mu sub p. But the other way of writing it is this, is that their difference is 0, okay? And so in this case, 0 is not in the interval. 0 is out here. So it is not a plausible value for the true difference and should be rejected. So 0 is not inside the interval. So it is not a plausible value for the true difference at 99% confidence and should be rejected. Make sure you can say the confidence level, because if you had a different confidence level, it could be in the interval. Okay, so so making the connection with the p-value, the low p-value below 0.01 also tells us to reject the null hypothesis. Okay. So that is the connection between the interval, the p-value, and the hypothesized value. Okay, and then our last context is this. So it says another doctor also wants to see if a new drug works in lowering cholesterol. He has 10 patients with high LDL take the new drug for a month, finds their improvement in LDL. Another time, the same 10 patients also take a placebo for a month and find their improvement in LDL. It is randomly decided whether they take the drug first or the placebo first. The results are shown below. A test of significance is done. Now, it may be tempting to do the same thing that we did here and do a 2 sample t-test. But the difference that you need to notice is that this data has been paired. This number goes with this number. It's the same patient. Okay. And so, whereas this data is not been paired. There's not, that 5 does not go with that 2. That 18 does not go with that 3. If you change the order of, like, let's say, of these numbers, move them around within each group, it would make no difference. We'd end up with the same thing. But when the data has been paired, what you've got to do is this. You're going to subtract all of the values, okay? And so in this case, I'm going to say drug minus placebo. And I didn't end up with any negative ones, but that's perfectly fine. Okay, if they are negative, then they're part of the data set. So I subtract all of these numbers, and we are going to do a t-test with the differences, a 1 sample t-test with the differences. So there we go. And so what is the null hypothesis of our paired t-test? Okay, so the null hypothesis is that, in essence, the mu of our differences is 0. Okay, the null hypothesis would be that there's no difference in the drug and the placebo. And if that's the case, then the differences would add up to 0. And any differences between the sample values and 0 would just be sampling variability. So mu sub d is the true mean difference, drug minus placebo. Make sure you state how you subtracted it. So I subtracted drug minus placebo in the LDL improvement for patients like these. These patients were not randomly selected. Okay, so you have to say patients like these when they take the new drug and the placebo. All right, and so then we're asked to find your test statistic and p-value. So this is what you do. You take your differences and you treat it as a 1 sample t-test. So we're going to enter them in list 1. So you go stat and edit, and there it is. I put the differences in list 1 there. Now let's find our test statistic p-value. So I hit stat and test, and just like we did for the problem earlier, just go to t-test. And in this case, I'm using data. The null hypothesis value is 0, no difference. All right, list 1, and let's see, the alternative is greater than. And so then we go calculate. And so there's my test statistic, and there's my p-value. Remember, that is scientific notation. This is 3.649 times 10 to the negative 4th. Okay, keep that in mind. So, which ends up being that. So it ends up being that number when you move the decimal point over 4 places. And your degrees of freedom is just we treat this just like a 1 sample deal. It's just your number of values minus 1, so it's 9. So there's our test statistic, there's our p-value, and that is it. Thanks for Thanks for watching the video. If you have any questions about that, then please let me know. I'll be glad to talk with you, and hope you're doing well. Hope you have a great day.